Mark your own. Here we go. Oh, my favorite student. Given the following pair of parallel plates, what's the magnitude and direction of the electric field? All right, so electric field, symbol capital E. Now I can find it this way. How do I know I wouldn't want to use that for parallel plates? Pardon me? There's an R that tells me that it's point charges. So voltage, the second definition, voltage divided by distance. It's going to be, what is the voltage? Not 500, not 250, 750. From negative 250 to positive 500 is 750 volts. Now, if you use the wrong voltage, you'll get 1.5 out of 2, and you'll say, oh, yeah, I better be more careful. I did give you the distance, and I also told you on your test almost every time you'll also have that distance there as well, just to try and trick you or confuse you. Don't use that one, but they'll give it to you, especially if it's a multiple choice question, because I need to give you 4 good wrong answers that can show up somehow. So this is going to be 750 divided by 0.055. By the way, again, the reason it's 750 is technically it's a change in voltage. You started at negative 250, you ended up at 500, you must have traveled through 750 volts. So, yoink, 750 divided by 0.055. Well, not very convenient, but that's okay. 13,600 volts per meter or newtons per coulomb. That's the magnitude. Direction. Which way would a positive sitting right here want to move if it could? Towards the negative. Down. So in terms of marks, I would probably go something like this. Half mark, half mark, half mark, half mark. So if you botch that, you can get 1.5 out of 2, because I'll assume you wrote down the right equation. I'll assume you did your math correctly. 2 numbers. I hope I can assume that. And then if you got the direction right, there's your half as well. If you got the direction wrong, then you can get 1 out of 2. Suppose an electron is placed at location A at the bottom of the diagram. What will its final speed be when it hits location B? Which way does this electron want to fall? Does it want to, if we put an electron at location A, does it want to stay there? Why doesn't it want to stay there? Because location A is negative. Location B is positive. So it will fall up. It will speed up. Okay. Is there a change in height? Is there a change in speed? This is a job for conservation of energy. I think we're starting at rest. And I think when we get to the top, that's like hitting the ground. We've used up all of our potential energy. Now, I also would have no problem giving you this same question not starting at rest. We did a couple in the homework where the electron had already been accelerated and then entered this region and got accelerated or more accelerated. Anyway, sped up. Okay. Here, well, kinetic has been a half mv squared for quite a while. I'm going to use Q times the voltage. Now, if you use the same voltage as part A, in other words, if you didn't use 750, you'll get 4 out of 4 on part B. I'm not going to penalize you twice as long as you did all the arithmetic correctly. I want to get V final. I think V final is going to be 2 times Q times the voltage divided by the mass square rooted. By the way, food for thought without doing the arithmetic. What if I put a proton here and I put an electron here? Which one will be traveling faster when they get to the other side, or will they be traveling the same speed? There's the equation that determines the speed. Let's see. Do they have the same charge? Yeah, one's positive, one's negative. Do they go through the same voltage? Yeah. Do they have the same mass? Which one's heavier? So which one's going to be traveling faster? The electron will be. Same change in energy? Absolutely. Same speed? And this is again where our gravity analogy breaks down. Not so much. Okay. Food for thought, just kind of thinking out loud. It's going to be, yoink, 1.6 times 10 to the negative 19. Technically, the electron is negative, but it's inside a square root, and I want to take a positive answer anyways, so okay. Mass, is it 9.11 times 10 to the negative 31? I kind of have those memorized again during this unit, and I'll forget them again in a month or so. 2 times 1.6 times 10 to the negative 19 times 750 divided by 9.11. Whoa, that's faster than... Oh, wait, square root. Do you get 1.62 times 10 to the 1, 2, 3, 4, 5, 6, 7? No, yes, yes, I hope. No? Am I wrong? Did you get that?
Oh, I got the wrong voltage.
Oh.
Yeah.
Is this right? Okay. Okay. 1.62 times 10 to the 1, 2, 3, 4, 5, 6, 7. 1.62 times 10 to the 7th meters per second. In fact, in this case, I could even ask you for the final velocity instead of the final speed, because the final velocity would be, I could give you a direction, up, but speed, because that's a scalar approach. Okay? If you got that right, great. Otherwise, hey, look, probably 1 mark, 1 mark, 1 mark, 1 mark. And again, if you used the wrong voltage, but you did all your arithmetic correct, I'll give you 4 out of 4 on part B. I penalized you on part A. Turn the page. We did turn the page, didn't we? Excellent! We learned! You knew that was coming. Come on, you knew that was coming. Okay, here we go. Good, now you won't do it again. Mission accomplished. Oh, I said, yeah, I can have it going. Suppose an electron is traveling with an initial speed. Now, this question here, I asked you for the final speed. The other thing I could ask you for is I could give you the final speed that I want and say, hey, how much voltage do I need? Or I could give you the final speed. Nope, never mind, that's all. I was going to say I could do an electric field question, but probably not. That would be awkward. So again, potential energy. Again, you use up all of the potential because you've fallen all the way through the plates. You have no more extra energy to speed you up with. It's all turned into kinetic. That's all I can cancel this time. This is going to end up being a half mv initial squared plus m, no, Mr. Dewick. Sorry, I've just finished energy with my physics 11s. That's in my brain. QV equals a half mv final squared. This isn't too ugly. I think here I'm going to get the v by itself. So I'm going to go times, 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 cancel, cancel. And I get mv initial squared plus 2q voltage equals mv final squared. Lots of room. V final is going to be m v initial squared plus 2q voltage divided by m square rooted. Now, how can I change this question as well? I might give you a proton on the test, so just make sure you read carefully. The charge won't change, but the mass, right, Jordan, certainly will. Don't always just use the mass of an electron. See, what else could I do? I guess if I really wanted to get esoteric, and I don't think I did, I could give you the initial speed, the voltage, the final speed, and say find the mass of the charge. Could solve for m. There's 2 of them. I'd get them to the same side, and then I'd probably factor out the m to get a single m. I don't think I've ever asked that. I mean, I could. I don't think it's gonna. I don't think it shows up anywhere. Partly because there's a much better way to calculate the mass of a particle, and that's to put it in a magnetic field and bend it in a circle, and you can get it from the radius. So, yeah, take that back. I don't think I'm going to ask that. Speaking of, what am I moving, proton or electron? Electron. Big square root. 9.1 times 10 to the negative 31. Initial speed, hello, 2.1 times 10 to the 5th. Plus 2, 1.6 times 10 to the negative 19, as I'm running out of room here. The voltage, oh, this one, 150. Oh, mass, 9.11. Here we go. Yo. I forgot to square it. Really? So you should be yelling, squared, at me? Wow. Terrible, Mr. Dewick. Awful, Mr. Dewick. I never make mistakes, right? 2.1. Squared plus 2 times 1.6 times 150 equals divided by 9.11 equals, good, nice big value, square root of that. Do you get that? 7.26 times 10 to the 1, 2, 3, 4, 5, 6. So if you got that, of course, 7 out of 7. Otherwise, 1, 2, 3, 4, 5, 6 lines of work. That'd be nice. Oh, you know what? I'll go like this. 1 mark for that. 1 mark for canceling out PE final. 1 mark, 1 mark, 1 mark, 1 mark, 1 mark. There's your 7. Something like that. Okay. Can you give yourself a nice, lovely score out of, count 'em, 7 and 6, I guess, out of 13? Does yours have a little out of 13 at the top or not? No. Note to self. Add that. So, questions from the homework from last day. I have been asked to do number 3. I just glanced at it. Maybe it's a bad question. Okay. An electron beam is accelerated by 1500 volts, which means I can find... Oh, I assigned 3? Okay. I shouldn't... 3 is overkill, but let me tell you how it's going to work. I can find the initial Vx that the electron enters the beam with. And that's going to be from the acceleration of 1500. In fact, it's going to be all of the potential turns into kinetic. In fact, it's going to be, we did this one just on the quiz, 2qv divided by the mass. That's going to give me how fast it's traveling straight sideways. Okay? I can also find time that it takes to travel. How long is this? 3.5 centimeters. So 0.35 meters. So I can also tell you how long it's between the plates for. I could also find the acceleration that it's getting pushed up at. That's going to be from this voltage. Sorry, guys, I didn't read that question carefully at all. I should have looked and seen that there was a angle answer. I mean, okay. Since I know time, and I know the acceleration, the acceleration, I'd go electric force equals ma. What's electric force? QE. I don't know the electric field. Voltage divided by distance, I could find the acceleration. And VI is 0. I could tell you what the vertical component of the velocity is, and then that's what they want you to find. They want you to add those two together, tip to tail, and you can find a resultant in theta. That used to be part of the curriculum. It was kind of a neat question. It's a little overkill as far as I'm concerned. So, you know what? Nuke number 3. My bad. I apologize. Boy, I didn't read that carefully. Yeah, 6 is this. I caught the other ones, I thought. I think. Oh, well. Any others? You followed my explanation? Okay?
Yeah.
I mean, it could be done. It's just overkill. Yeah, I'm not going to give you... I've tested... other reason as well. I don't want a kid who struggled with vectors to lose more marks because they struggled with vectors when I already took marks from them if they struggled with vectors. Is that all right? Yeah. Any others? Okay. So, the next unit, lesson 1, Ohm's law. Hey, here's what you're going to learn. A bunch of this stuff here. That's from the learning outcomes, but let's jump in right here. Voltage. The other nice thing, this is kind of a nice review. It's more charged stuff, so it's not like I'm going, you're teaching me new stuff. No, we're getting you to think about the same stuff in a slightly different way. Fill in the following key facts about voltage. What was the definition of voltage? This you can get from the electrostatics unit, looking at your formula sheet, looking at the first time voltage appears. How did we define it? It's on the left-hand side. I think it's the second one on the left. Go down. Second row on the left. You're right, Sean. Voltage is defined as, do that. How much energy per coulomb. It's the ratio of how much energy does the battery have? How many extra coulombs of charge does it have? That's its voltage. How many volts? 1.5. Where's my AA or AAA? How many volts? 1.5. Same voltage. Which one has more electrons to spare? The bigger one. Which battery will last longer? The bigger one. These can both power the same device. This one, though, would burn itself out pretty quickly. Why don't we just always go with big, huge D-cell batteries and everything then? Yeah, we like our technology small, right? Units, volts, right? As an equation, we said this. Voltage is PE over Q. That was the actual equation that shows up on your formula sheet. What was the other dumb word for voltage that I hated? So, what happens inside a voltage source? What's going on in a battery? Well, the simplest explanation is work is done by separating with an A there. I think separate has an A there, doesn't it? Separating charges. Through some kind of chemical reaction, we can get positives over here and negatives over here. It's more complicated than that, but that will suffice. Now, they're unlike charges. What do unlike charges do? Unlike charges, please think very carefully, unlike charges attract. They would like to be attracted towards each other, but we prevent this through some type of medium, some type of physical or chemical barrier. So we're going to say, you guys want to get back together? We're going to force you to go through wires through a circuit. The circuit symbol for a voltage source, symbol for a wire is a straight line. The symbol for the negative end of a battery or a cell is a short vertical line. There's the positive. That's the symbol for technically a cell, not a battery. A battery is two or more cells, but I'm going to use those terms interchangeably because we do in society. But technically, that's a cell. Technically, that's a battery. The standard chemical reaction we can get very easily is 1.5 volts. That's why you'll see 1.5 volt batteries, you'll see 3 volt batteries. Hey, the square rectangular batteries that you like to touch to your tongue to get a shock, what's the voltage in those? 9, it's 1.5 times 4, not a coincidence. What's the voltage in a car battery? Not 13, not 11, what? Nobody's in mechanics? None of you? Boy, did I hit the wrong crowd. 12. Car batteries are 12 volts. Again, a multiple of 1.5. We can, that particular chemical reaction, we have good control over. To understand what's happening in electric circuits, it's very helpful to have a mechanical analogy. Just like in the last unit, I tried to flog gravity quite often and say, look, this is sort of like gravity. The analogy I'm going to use here is a ski hill. Recall, in the previous chapter, we said the gravitational analogy of voltage is height. What you can think about in a circuit is a battery is like a chairlift, in that the same way a chairlift, when you go skiing, lifts you to a higher energy state, more potential energy. And then how do you lose that energy? Go ski hills, bleed off the energy. A battery raises charges to a higher energy state. The resistor is where you bleed off that energy. And that resistor can be a light bulb, it can be your smartphone, it can, whatever electronic device you choose to pass the charges through. The ski hill gives you, the battery gives you more energy, raises your height. The ski hill, the resistor, reduces your energy back down. In fact, that's going to give us one of our important points. Don't write this next bit down. But if this is a 6-volt battery, and the charges are traveling in this direction, and right here is ground level, if you leave the ski hill with 6 volts, how much must you lose in that resistor in order to get back down to the ground? Exactly how much? 6 volts. This is how we're going to start to analyze circuits. We're going to use this ski hill analogy. Okay? So, the voltage at a point in the circuit is like the height at a certain point in the mountain. The voltage gain is like the height the skier gains on a chairlift. In fact, you're going to hear me often just call batteries chairlifts. The voltage drop is like the height you lose going down a ski run. Electric circuit. Hey, what happens if I connect a wire to one side of a voltage source? Oh yeah, turn the page. What if I took a battery and I touch a wire to one end of it? Well, electrons will repel each other, and I might get a few extra electrons there, but not very many. Why? They got nowhere to go. And as soon as I get a few extra electrons, they're going to start to repel the rest of the electrons and not allow any to come. Why, Riley? Because like charges do what? Like charges do what, Riley? Much like you are right now. Yes, repel. Right? So you'll get a few extra electrons, but nah. But what if it forms a continuous loop? Now the electrons can flow. Now the electrons can flow, and they can go rejoin the positives. Now we have current. And that the definition of current is moving charges. What's the problem with part B? We call this a short circuit. Because in terms of a circuit, I have my chairlift, let's say 6 volts. Is there a ski hill for you to lose your energy in? Is there a resistor for you to lose your energy in? But you must, because you're getting back to the bottom of that battery. Where are you losing the energy in? You're heating up the wires. The wires will heat red hot. Fire bad. This is why there's electrical fires fairly often with bad wiring. Your stove elements, by the way, are a controlled short circuit. That's all they are. Okay. Why is this a better circuit? So if you gain voltage here, whatever voltage you gain right in the battery, you can lose it in the light bulb. In fact, the analogy I say is, this is a lovely ski run with one hill. It's not a short circuit. This previous one, you're skiing off a cliff because there's no resistor, but you got to get back down to the ground. That's not a healthy ski run. There's no gentle ski slope for you to lose your energy off of. Okay? We're going to be reinforcing this over and over and over. So if you're a little lost, don't worry. Current. This is your first equation on your formula sheet. Electric current is defined as the rate of flow of charge in a circuit. Anytime I talk about a rate, what I'm really saying is divide by time. Power was the rate at which work was done, divide by time. Acceleration was the rate at which your velocity was changing, change in velocity divided by time. Oh, and charge. Current is charge over time. We will hardly use that equation. We will use that to derive other stuff. But once in a while, I may actually say, hey, okay, how many electrons have come by in 10 seconds? Oh, an electron has a charge of 1.6 times 10 to negative 19. So find out how many 1.6 times 10 to negative 19s have gone by in that time. Oh, in fact, I said, recall any charge Q is a certain number of fundamental charges. So Q is the number of electrons times the elementary charge. That's what I wrote here when I said Q equals NE. If you know the charge in coulombs and you actually want to find out how many electrons that is, divide by 1.6 times 10 to negative 19. Okay? So we can relate current to the number of electrons that have moved through the circuit. You want to find the number of electrons, take the charge, divide it by 1.6 times 10 to the negative 19. Example 3. A 1.5 volt AA cell is rated at 750 amp hours when connected to the motor in a portable CD player. The cell provides 0.250 amps of current. A says, how much charge is stored in the cell? What equation did we put in the box right above?
I is equal to Q over T.
What's Q a variable for? Charge. You know what? Oh, by the way, current is measured in coulombs per second, and we call that an amp, named after Ampere. Did a lot of work with electricity. Okay. I should have mentioned the units. Let's go back here then. It wants the charge. Okay, Riley, get the Q by itself. Yes, Riley, you got a question right. Riley, by the way, what's I measured in? What's T measured in? You know what? This is amp hours. That is also I times T. I think that's the answer to this question, except I just have to go from hours to what? So I'm going to say this is 0.75 amp hours. I want hours to cancel. I want seconds on top. How many seconds in 1 hour? Okay, remember doing this from Physics 11? Holy smoke. Okay. And the reason I was able to do this is I noticed really what we're saying is charge is current times time. I said, hey, that's a unit of current time. Not the preferred one, but you know what? Rather than do anything funky, I think I can just do a conversion on that. How many coulombs of charge does this battery have? 0.75 times 3,600. It has 2,700 coulombs of charge. That may sound like a lot. It's not going to discharge all at once. Hey, how many electrons is that? Well, the number of electrons is the charge divided by the charge on one electron. It's going to be 2,700 divided by 1.6. And these are going to be really big numbers because, hey, this has several probably trillion, or maybe even what's after trillion? Quadrillion, or it might be quintillion. It's got a lot of electrons stored in here. Electrons are small. Divided by 1.6. And I should be fussy. It has more electrons than that. Really, the question is, how many extra electrons does this battery have? Because there could be some that are paired with the protons and they're neutral and I can't use it. Okay. 1.69 times 10 to the 22. Of more interest is, how long will the cell power the motor? Well, let's see here. I guess if I equals Q over T, I guess T equal, although they haven't really, you know what? What are the units for that number there? Read me. What are the units for that number there?
Amp hours.
Amp hours. If I divide by amps so that amps cancels, what will I be left with? Hours, which is a measure of time. I think to find time, I'm just going to go 0.750. You know what? Don't write it out, Mr. Dewick. Amp hours divided by this CD player. How many amps of current does it require? This CD player, how many amps of current does it require? 0.25. How long will this CD player run off this battery? Whoop. Yeah, you'll get 3 hours of battery life. Now, I always do this question because to me it's kind of interesting. You guys kind of like to know, how do they figure out how long devices will last? An amp hour, if you get into electronics, is a very, very common unit of measurement. It tells you an awful lot about, well, it lets you make rough estimates as to how long batteries will last. In fact, everybody who's in electronics, who's building devices, who's building components, or if you're, for example, a boater and you're running your boat off of power camping and you want to, out on the ocean, and you want to know how long your power will last. What you want to know is how many amp hours your battery has, and then how many amps you're drawing. Divide, that's when I better be back on shore. I am not going to ask you this question, so you can make a little note here. But cool. Amp hours is not really a unit we're going to be using for the remainder of this unit. Let's go back to our ski hill. So in our ski hill analogy, voltage is like height current is like number of skiers. Our ski hill analogy is going to break down in that we're going to make all the skiers ski at the same speed. But number of skiers. Put it on block A. Thanks, kiddo. So I wrote here in the ski hill analogy, the flow of charges in a circuit coulombs per second. It's like the flow of skiers up and down a ski hill. Number of skiers. Since electrons flow at a constant speed, we're going to assume the skiers use their skis to control their speed and move down the hill at a constant speed. Okay, fine. Problem. Electrons flow this way. And this is where the fact that Benjamin Franklin named positive charges and negative charges incorrectly, that he should have named negatives, electrons, positive, and he should have called protons negative, comes back to haunt us. Electrons flow, Riley, from negative to positive. But we would like to say that the voltage, the battery moves charges uphill and the resistor bleeds energy off downhill. And so we would like to be able to say that although electrons go from a lower voltage to a higher voltage, we would like to say that current flows downhill from a higher voltage to a lower voltage. And that's what we're going to do. Conventional current is which way would positives move if they could, even though technically the positives are locked inside the nucleus. From now on, when I'm talking about current, when I'm analyzing a circuit, unless I specifically say which way are the electrons moving, if I say current, you say, oh, it's from positive to negative. The math is much nicer. It's much easier to keep track of. So I wrote, for this reason, we choose to focus on the positive charges, the nuclei. And I guess mathematically, having electrons flow uphill mathematically is the same as having positives flow downhill. Although the positives don't actually move. So what we call current then is actually the downhill flow of positive charges. Many books will call this conventional current. If I ask you about electron flow, from negative to positive, but if I ask you about current, start at the positive end. In other words, example 4 says, draw the direction of electron flow. I'll do that in red. Electrons flow that way. I'm never going to use that again unless the question specifically demands it. And it will on your test. One multiple choice question will say, hey, which way do the electrons flow? But from now on, because it's so much nicer, I'm going to say current, which I'm going to do in blue, flows downhill from the top of the battery, from the positive to the negative. We're just going to define it that way. Much nicer. Now we come to equation number 2, Ohm's law and resistance. Every circuit offers some resistance to the flow of charge. Wires have some small resistance, although, Amanda, we're going to pretend our wires have a resistance of 0, which is why that short circuit is so bad. The circuit symbol for a resistor is a series of short, wavy angled lines, which you should recognize from science. Used to be science 10, now it's science 9. And resistance is due to, I guess, sort of electric friction, where the electrons are colliding with other atoms in the material that they are passing through. And when they collide with the other atoms, the same way as when you rub your hands together, some heat is created, and so that heat's got to come from somewhere. It comes from the energy per coulomb that the electrons had. They pass off some of their energy to the resistor in the form of heat or other way. We're very clever. We can bleed that energy off into a number of different ways. Since the electrons lose energy, that means there was a voltage drop across the resistor. Okay? For example, you might be coming in at 8 volts. You leave at 5 volts. How many volts did you lose going through the resistor? Meant to be really obvious. You lost 3 volts going through the resistor. This would be a voltage drop. Now, it's always going to be a voltage drop, so we're almost never going to write that negative in front of the 3. It's going to be, if you write a voltage on a resistor, I'll clue in that you and I know you're losing voltage because you lost energy, and voltage is energy per coulomb. It's negative. Just it's not labeled with a negative in any diagrams. Never is. We want to quantify this, though. We want to be able to calculate this. Right now, I've just been making up numbers. Let's see if we can actually calculate numbers. The amount of flow through the circuit depends on the total amount of resistance and the total voltage applied. What can you say about the current flow, about the numbers of skiers in each case? Fill in either large current or small current. High resistance. Let's imagine this hallway behind me, my classroom hallway here, is really, really crowded. And we want to get students to be able to sprint through. High resistance would be a really, really crowded hallway. Do you think that would give us a bigger current, more students being able to sprint through, or a smaller current, fewer students being able to sprint through if the hallway was crowded?
Smaller.
Or you can think about, instead of the hallway being crowded, somehow magically us narrowing the hallway so it's only one person wide. You're not going to get much current. Low resistance. What if I empty the hallway? Or what if I make the hallway really, 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 really wide? What if you have a big voltage drop, a high voltage? What if you got a really, really tall chairlift? More popular, less popular? More popular, more skiers, higher current. Small voltage drop. Again, you don't need to know these four things. What these are going to do is help us derive the equation. It says write a word equation. You know what? I'm going to give it to you here. V equals I times R. You guys saw that in Science 9. This is Ohm's law. This is the big equation. This is the one we're going to be using on about 90% of our circuits that we analyze. This is the one you'll all end up memorizing because you get sick of looking it up, and it's a fairly easy one, V equals I times R. Where V is the voltage drop across the device, I is the current flowing through the device, and R is the resistance, and these are all scalars. What that also means is if I know any two, I know the third. If I know any two, I know the third. Technical comment, if I want to be consistent with the previous unit, I really should write change in voltage, and it really should look like that, but the notation is so cumbersome, you've already noticed there are times in physics where we just say, let's get lazy and just, time, we don't write delta in front of anymore, so we just write it like that. Okay. The units of resistance are ohms. The symbol, oh yeah, turn the page. The symbol for an ohm is a little mouse hole in a wall. It's a Greek letter, omega. That thing there. 1 ohm of resistance means that you'll lose 1 volt if you send 1 amp through it. That's its definition. In fact, if V equals I times R, get the R by itself. So 1 ohm would be, you lose 1 volt for 1 amp, what it's worth. Good conductors have low resistance, wires. Poor conductors, insulators, have large resistance. So again, I like to try and give you an idea of what's really big and what's really small. So I have some mixing and matching here. Let's see if we can reason our way. It says mix and match typical resistances. So on the left-hand side, I have a bunch of stuff. On the right-hand side, I have a bunch of resistances. Which of those do you think is the best, on the left, is the best insulator? Which of those do you think lets almost no electricity pass through it? Which of those would have the highest resistance? Look at the list. Look at the list. The left-hand side. Look at this list. Which of these would have the highest resistance and let almost no electricity pass through it? No, we're not too bad. Glass is a great insulator. That's why we use it, for example, on power lines to surround the wires when we connect them to the metal poles. Some type of ceramic. Glass is approaching an infinite resistance. You can force charge through it with a big enough voltage and a big enough current. Can be done. But it's basically a perfect insulator. And easy to make, and we can melt it and shape it. Very handy. Which of these do you think has the lowest resistance of the ones that are remaining? Look at the list. Copper wire. What's the lowest resistance on the right-hand side? No. On the right-hand side, what's the lowest number? What do you think would go with the copper wire? Yes. You guys forget we're going to use a process of elimination here, right? Cross that guy out. Mix and match typical
Okay, now I know that.
Okay? We're going to match these to those, but we're going to do a process of elimination. Glass, very high resistance, nearly infinite. Copper wire, you know what? We're going to pretend it's 0. Okay, it's a 0.1. We're going to pretend it's 0. Which one do you think is the next highest, the biggest? Well, let's think. Light bulb must have some resistance. Why? Because what does it say in brackets next to the word light bulb? Think thin hallway. That's going to be, okay, let's come back to that. Electric motor, coils of wire, average lab resistor, human skin. Turns out, actually, human skin is not a bad insulator. Human skin has the next most resistance. Inside, we're mostly liquid. But outside, our skin's not too bad. Human skin has a resistance of around that. Next. The next highest is going to be, of the remaining devices, the one that gives off the most heat. Why? Because the electrons are rubbing against each other so much because it's such a high resistance that they're causing it to, here's your hint, glow white hot. Light bulb. The last two, your average lab resistor and electric motor. Turns out your average lab resistor is usually around 200 ohms. An electric motor, because electric motors don't give off much heat, a little bit, we want them low resistance. Those ones I'm not going to freak out about. What I do want you to realize is, okay, we do have some substances that are nearly infinite resistance. We call those insulators. Hey, what's something else that's a great insulator that doesn't conduct electricity? Rubber, it's why rubber gloves for electricians. Styrofoam, all plastics, okay? Those would have nearly infinite resistance. Copper wire, gold, in fact, actually copper isn't the best. Gold and silver are even better, but they're pricey, so copper is the cheaper alternative. But you'll notice copper wire is getting swiped from buildings fairly often now. You see it in the news, right? People are going to an old abandoned building, or a not abandoned building, and just ripping out all the wire at night, selling it on the black market. Copper, low resistance. Again, I'm doing bad physics, so technical comment. As the wires get hotter, the resistance increases, which makes the wires hotter, which makes the resistance increase. Resistance changes with temperature. We're going to pretend that doesn't happen. Let's talk about electrocution. Human skin is a good insulator, typically tens or hundreds of thousands of ohms. But it will only protect us up to a certain point. When the voltage exceeds a certain value, the skin will break down. It will ionize just like air does. There is a big enough electric field that will cause your skin to ionize, and now it'll pass electrons from one skin cell to the other. And on the inside, we're basically salty water, which conducts electricity really well. Once beyond the skin, the danger to our health lies in two effects. First, there's the heating up of tissue as electricity flows, because electricity causes resistance, causes electric friction. This is why when you get electrocuted, it can cause severe burns, can destroy internal tissues and organs. Secondly, the flow of electricity through the body can disrupt the body's own electrical nerve impulse, leading to temporary freezing or jerking or loss of control of the muscles. When those muscles are your heart and your diaphragm, your ability to breathe, your lungs, that's bad. That's danger. Once beyond the skin, the heating effect grows larger with large currents. To burn yourself from electricity, you need to get a fair bit of current into you. However, to cause your muscles to twitch helplessly, you don't need very much current. The muscle paralysis is most pronounced around 100 milliamps, which is around, it's called the death current because that'll cause your heart muscle to fibrillate. 100 milliamps, not very big, so here's the moral of the story. Okay. About, oh good gosh, probably 20 years now. My uncle almost died. He was using a voltmeter that was defective. It had a short circuit in it, and he was using it to check the voltage of, it was a farm with a huge freezer that cooled off the entire building, and the building was about twice the size of our school gym. So this particular electric motor was running an awful lot of current through it, and it was malfunctioning. So he was testing out parts with the voltmeter, with a faulty voltmeter, and he took, we figure, probably about 100,000 volts and probably about 30 amps, which is normally fatal, through him. And it burned most of the skin off of his face. What really scared him is when the electricity went through him, because he now became a short circuit, it blew the fuses in this building with no windows, which meant all the lights went off right when he got shocked. Now, he didn't know the lights went off. What did he think had happened? He thought he'd been blinded. And so he spent about 5 minutes on hands and knees fumbling, because also he's in shock. His muscles aren't working properly. He crawled his way to the door, and he says, like, he remembers opening the door, and his eyes were still sore, but just seeing daylight, oh, thank God. In the main office, about 50 meters over, the lights dimmed and went on. People went, what the heck was that? It's odd. So someone went wandering out, and he ended up being okay, but he still has scars on him from this. So be careful in dealing with electricity. And he knew what he was doing. Faulty voltmeter. We suggested, but it's hard to prove, because they're going to say, can you prove that you hooked it up right? Where's your witness that you hooked it up right? How do we know that you weren't touching something when you hooked it up? It's not as easy as you think. And the moral of this, the most important thing was, he's okay. Right? So, in our ski hill analogy, resistors are going to be like the ski slopes. The battery lifts you up, chairlift. How do you get down the mountain? You have to go through the ski slopes. You don't have resistors. You don't have any resistors, that's a short circuit. That energy is going to go up into heating the wires. It's going to make the wires red hot. That's bad. The amount of resistance is sort of like the depth of snow. High resistance means really deep snow, really big powder. You can't ski as fast. Low resistance, usually means smaller current. Low resistance means, hard packed snow, it's icy, although the skiing conditions aren't as good because people like powder. This is where my analogy breaks down. You can go faster, you can get more skiers through there, more current. So what Ohm's law for ski hill states is, the flow of skiers, current, varies directly with the height of the mountain, higher voltage, higher chairlift, more popular, varies inversely with the snow depth, the resistance. Current equals V over R, which is V equals I times R rewritten. Example 7 says, find the current in each case. Okay. I always go and I always identify the battery, and I always draw an arrow pointing in the direction of the current, because that's how I'm going to ski down this hill. How high is this chairlift? Not meant to be tricky. How high is this battery? 6 volts. How high is this chairlift? 6 volts. There's my analogy. So let's try that again. What's the voltage? How high is this mountain? How high is this chairlift? What's the 6 volts. Now, for you to ski through here, you have to get back down to 0 at the bottom of the chairlift. How many ski hills, resistors, are there? So how many volts must you lose going through that resistor? You must lose 6 volts. Now look at that resistor. Do you know the voltage? Do you know the resistance? If you know 2, you know 3. What's the current flowing through this resistor? How many amps? Someone do it, please. It's going to be 6 volts divided by 25. Sorry? 0.24 amps. Now compare that with, look at this second circuit. No resistor. What do we call this? A short circuit. So there is a resistor only from the wires. Okay? Current equals voltage divided by resistance. How many volts are we going with? 6-volt battery, not a very, by the way, 6-volt battery is those rectangular ones that they clamp onto the bottom of big flashlights. Okay, so not a big battery here. What's the resistance? How many amps are going to flow through these wires? These wires are very rapidly going to get red hot. These wires will very rapidly melt the insulation off of them. These wires, if they're then touching any wood, if this was in a house circuit, fire bad. This is how you start a fire. Don't muck around with electricity if you don't know what you're doing. Okay. Also, because current is charges per second, if you did just clamp one end of a wire to the other end of the battery, you're going to drain that battery really fast. Now, how long would this battery last? Minutes, probably. Okay. So, technical comment. We're doing some technical stuff here, obviously. The second diagram is an example of what's known as a short circuit. It's called a short circuit because it has almost no resistance and therefore will experience very large currents. Depends on the voltage source. Okay, if you short circuit a little AA battery using lab wires, you'll quickly drain the cell, but meh, no big whoop. If you short circuit a car battery, that's got enough charges and that's got enough voltage, you'll get yourself a fairly nasty shock. You'll jump back. You may burn yourself. There will be sparks. If you short circuit your house plug, well, ideally what your house plug has are fuses. And what fuses are designed to do is as soon as they see a spike in current, they melt, or now we use breakers, they flip the switch off so that you can't get the wires to heat up. Most breakers either flip at 15 amps or at 30 amps. Those are the standard ones. Cars, boy, none of you in mechanics, since you didn't know it's 12 volts. So cars have these little metal fuses. If you go look, you'll see it in the circuits, there's a little thin piece of metal, and that's designed that if the current spikes, it'll heat up and just melt. And when it melts, it falls apart. That breaks the circuit. No more electricity will flow. So you need to know where your fuse box is on your car. How many of you have blown a breaker before? How many of you were stupid enough to then turn it back on and replug everything in, assuming the same thing wouldn't happen? Okay? Whatever circuit you've just set up, you're demanding more than 15 amps or you're demanding more than 30 amps, and your house is saying, I can't do this safely. Unplug other stuff first. How much more have I got? Am I nearly done? Yeesh. Yeah, we're going to go because I'm not giving you any new homework, really. Electric meters. So how do we measure all this? You measure current and voltage with ammeters and voltmeters. What do voltmeters measure, do you think? What do ammeters measure? They used to be called amp meters, but over the years that just got awkward to say. So over the years it got shortened to ammeters. Easier to say, measure amps. Hey, what do you think an ohm meter measures? Resistance. Okay. Then you can actually purchase what are called multimeters. Multimeters are very clever devices that can measure all three. You flip a switch and now it'll measure current. You flip a switch and now it'll measure voltage. You flip a switch and now it'll measure ohms. I don't think we have any multimeters. I have voltmeters and ammeters on the shelves back there. These are nice analog ones that don't require batteries. The digital ones are in many ways much nicer and more convenient, but most of them require batteries and they're pricey. Consider the following circuit. So here's my real circuit. 6-volt battery powering a light bulb. Yeah, here's the schematic drawing. We're going to use the schematic drawings. For me to measure the current, what was our analogy? What did I say current was in our ski hill analogy? Number of skiers. I have to create a gate that all the skiers have to go through. I would not want to measure current, don't write this down, by putting an ammeter like that, because most of the skiers could go past me and I wouldn't know it. If I want to measure current, I have to physically break the circuit, cut the wire, let's say right there, and actually wire in an ammeter, and that will let me count all of the skiers. Don't write that down. We're going to do that later. Okay? What did I say voltage was on our ski hill analogy? The height. To measure height, you need to have a top and a bottom. If I wanted to measure, say, the voltage across this, what I would actually do is I would say, put a wire there, put a wire there, put a voltmeter there, and see how high I am right here, how high I am right here, subtract, that's the voltage, that's the height. So voltmeters, you don't want all the charge to go through. In fact, you don't want any charge to go through a voltmeter. Ammeters, you want all of the current to go through it. So let's talk about this. We said this. To properly measure current, the ammeter should be connected so that all of the current in the circuit runs through it. And on your test, I'm going to give you multiple choice questions where I give you pictures of several circuits with meters in them, and I'm going to say, hey, circle the one that has been wired correctly. Okay? For an ammeter, if I wanted to measure the current going through this circuit, I could put the ammeter there. By the way, I could also, if I wanted to, put the ammeter right there. I could also, if I wanted to, put the ammeter right there, because in all of those locations, every single skier, all of the current has to go through there. There's no forks in the road. So we need to break the ammeter, and we need to insert the ammeter. This is a word you're going to become very familiar with later on. This is where I always introduce it. In series. Series means all the same skiers flow through. This is correct. Yay. This would be incorrect. Boo. Riley, this is incorrect. Correct, Riley? Incorrect. Correct? Incorrect. For an ammeter. And can you see the problem? Because if ammeter is a number of skiers, you guys could go skiing through there, and the gatekeeper who was counting wouldn't know, because he hasn't been able to count the skiers that have gone through his gate. Compare that with voltage. To properly measure voltage drop, the voltmeter should be connected with one lead on either side of the change in height that you want to measure. It should be connected in parallel. And in fact, here's what else we say. We say, don't write this down, these wires should have an infinite resistance so that no skiers will actually go through here, because that would change the current, which would change the voltage, which would change the question. So voltmeter we want measured in parallel. Correct? That would be correct for an ammeter. That's correct for a voltmeter. This would be correct for a voltmeter. This is correct for an ammeter. I think it's my last little rant. Yes, and I'm done. You guys have been very patient. We've focused our introduction on direct current, current moving one direction. Abbreviation for direct current is DC. Our houses all have alternating current, AC, where the current goes this way, then that way, then this way, then that way. Who's in Math 12, pre-calculus? Where the current goes up and the current goes down, and the current goes up and the current goes down, and the current goes... Hey, what kind of a function is that? So, sine and cosine. Yeah, in fact, I can't cover alternating current in Physics 12 because I can't assume you guys have seen sine and cosine waves. But it's trig functions. Yet another application of trig functions is alternating current, okay? Everything that I show you works for alternating current. If any of you go into electronics, it's just you have to add a few more things. So much of what I've just said applies to alternating current. AC has a magnitude that varies as a sine function, and so it changes direction. The AC power has a frequency of 60 hertz. It changes directions 120 times in 1 second. Has a voltage amplitude of 110 volts. It's actually 113.4. And in fact, we're just going to say it's 120 volts because that's a nice, lovely round number to do our math with. Since we're being rough, our wires aren't going to have resistance. Since we're ignoring certain things anyways, we're going to say what comes out of the plugs is 120 volts. Okay? What's your homework? Well, you can work on this, but you're also working on the review. Number 2. Number 1. Three is good, so 1, 2, 3. I'm going to skip 4. Five is good. 6 is good. So 1, 2, 3, I skipped 4. 1, 2, 3, 5, 6. And they're all pretty quick plug and chug. Really, you want those done for after Easter break, but you can start to whittle away at them because I'm going to do part 2 of this lesson next class. Thank you.